Hi everyone, how are you all? So myself Nagappa, you are watching Appa Chemistry classes. Now our today's topic is Enantiomers and Diastereomers, and also I am going to explain in this video what is meant by Racimic mixture, okay, what is meant by Meso compound, what are a Racimic mixture, why they are, whether they are optically active or optically inactive, and most important I am going to tell you what are the formulas which we will use for the calculation of optical activity. So how many number of optical isomers are possible? In this video I will detailedly explain about one by one concept. So first concept in this video is enantiomers and diastereomers. What are enantiomers? What are diastereomers? And what is the difference between enantiomers and diastereomers? I am going to explain with neat examples. With the different examples I am going to take you. So now in the previous video we had seen the chirality, okay, optical isomers, why compounds will show the optical activity, and what is meant by chirality. Okay, chirality is nothing but handedness, so which are having the word unsymmetrical. It is also chiral carbon is also called asymmetric carbon. Those who not watched those previous videos, you can find those videos in the description of this video, as well as you can find in the icon of this video also. Okay na? So I won't waste your time. Let's get into the video of these isomers, enantiomers. Okay, enantiomers and diastereomers. What are enantiomers and diastereomers here? So in the previous video we had seen that if it has the organic compound has at least one chiral carbon, then it is said to be optically active. If it is more than one chiral carbon, then it may be optically active or it may not be optically active. It depends on the symmetries. Okay na? If that organic molecule has the any type of symmetry element like plane of symmetry, center of symmetry or axis of symmetry, so then that organic compound, even though containing chiral carbon also, it is optically inactive. If it is not having any symmetry element, then it is optically active. Now which type of these enantiomers are optically active? And most of the diastereomers are also optically active, which are not having any symmetry elements. So enantiomers also, if symmetry element is there, means they are not the optically active compound. Now what is meant by enantiomers, we are going to see here. Enantiomers are nothing but what? Enantiomers and diastereomers comes under stereoisomers. Enantiomers are which are non-superimposable on their mirror images. Non-superimposable on mirror images are called enantiomers. What is mean by non-superimposable? For example, it's my right hand. When I am placing it, it is in front of the mirror, it appears as left. Is it or not? My this thumb will be appear here, this small finger will appear in this hand. So that is what left becomes right, right becomes left. When I am standing here in front of mirror, if I am taking my hair with comb, then what happens? It will be in opposite direction. Okay na? So also you can see there in different, just whatever it may be, it must be an mirror image, and also it should not be superimposable. That is means the thumb, okay, it should not be appeared as it is. Okay na? It must be like this. Handedness. If I am placing like this, means I will get like this. Now you see here. So this small finger is matching with this one, and this big finger, this is a thumb which is matching with this small finger. So these two are what? Enantiomers. These are non-superimposable mirror images. Okay na? But whereas if you place the you take the one ball. So which has is that ball has any left and right? No, it is not having any left and right. Then what happens? That ball is symmetrical molecule. It is not said to be an enantiomer. Say for example, I am taking this pen and I am taking this hand, left hand. Is these two are mirror images? No, these two are not mirror images. Okay na? So it must be mirror image, and it should not be superimposable. Non-superimposable. Superimposable means whenever, say for example, is this pen has left and right? No, it is not having. It is superimposable on its mirror image. Okay, so if I am placing this my right hand, it will appear in the left hand. Okay, in the mirror. Then it is said to be non-superimposable. I think so you have understood what is meant by superimposable and what is meant by non-superimposable. Now let's see here. Enantiomers are stereoisomers which are non-superimposable on their mirror images of a compound are called enantiomers. Now simple example, you take here lactic acid. It is an lactic acid. So it is a lactic acid when we are placing here mirror. So now you see here the head, that is my head and my legs won't go up and down now in mirror. If we are seeing in the water, it will be different. Okay na? So in front of mirror, what happens? My head will be in the top only, my legs will be in the down only. But what happens? My left hand becomes right hand becomes left hand. And also my left ear becomes right ear becomes left ear. Is it or not? So here just left becomes right. That is head. This COOH and CH3 will be remains as it is. Now the OH is present here right hand side. The H is present in left hand side. The H will go to the right hand side. OH will come to the left hand side. That is what these two are said to be mirror images. And are they superimposable? No, they are not superimposable. Non-superimposable mirror images are called enantiomers. These two are called enantiomers. Now what is meant by diastereomers? We will see. So here the diastereomers are nothing but what? The stereoisomers of a compound which are not mirror images. They are not the mirror images. Say for example, it is pen and it is hand. Are these two mirror images? No. Okay, now if I am showing pen in the mirror, will be appeared as a hand? If it has appear means, you will feel that it is a ghost. Okay, so if anything is happening in our backside, then it will be like that. Is it or not? So here it should not be mirror images. Then they are said to be what? If they are not mirror images, they must be non-superimposable also. So stereoisomers of a compound which are not mirror images to each other and non-superimposable are called diastereomers. Non-mirror images, non-superimposable stereo compounds are said to be diastereomers. Now you see here, these enantiomers are having identical physical properties and identical chemical properties. Identical physical properties like melting point, boiling point, density, refractive index, etc. These all physical properties will be almost identical for the enantiomers. Now you take for the chemical properties also. Chemical properties also similar. They are having identical chemical properties. Identical chemical properties indicates the what? They forms the same type of compounds. Okay na? Say for example, this is lactic acid is there. This lactic acid and this lactic acid, whenever it react with other compound, both will forms the same compound. But the rate of reaction is different. Okay na? The reactivity will be different for the different isomer. So they are having the identical chemical property, which means they form the same products but differ in their reactivity, or rate of reaction is different. Rate of reaction is different. Okay na? Now these have different biological property, which is very important. Enantiomers are having different biological property. Okay na? Say for example, one medicine is prepared, which is an optically organic compound with one medicine is prepared. That medicine has some biological influence in a D isomer. In dextro form, it has the biological. Say for example, it is a lactic acid. No, it is take for example, it is a D isomer, dextro isomer. It is levo isomer. Okay na? So now this D and L are what? They are enantiomers. Now this dextro isomer has the biological active nature, but this levo isomer, it may or may not have that isomer. Generally, dextro is having biological activity, means levo will not have the biological activity. Due to that only, most of the optically active organic compounds which are used in the medicine, so one form will have the optical active nature, other form will have the optical inactive nature. So that optical inactive organic compound will be left over in our body as it is. Due to that chemical which is left over in our body, it creates the side effects. Okay na? Organic compounds are optically active, containing optically active organic compounds are used in the medicinal purpose. So in that, one isomer will be very optically active and another isomer is optically inactive. So that optically inactive will be left over in our body as it is. That chemical substance is left over in our body that creates side effects to our body. Is that clear? Now, next diastereomers properties we'll see. These are possible with more than one asymmetric carbon. Enantiomers are possible even with one asymmetric carbon also. Here only one asymmetric carbon is there. That is chiral carbon, only one is there. But whereas diastereomers are not possible with a single chiral carbon or asymmetric carbon. It is possible with more than one asymmetric carbon or chiral carbon. Now this shows similar but not identical chemical properties. These will show the similar chemical properties but not identical. Their rate of reaction will be different. Now these have different physical properties. These diastereomers have different physical properties like melting point, boiling point, density, refractive indices, like that. These can be separated easily by fractional distillation and fractional crystallization, and also by chromatography techniques, etc. By using these techniques, these diastereomers can be separated. And also here the geometrical isomers comes under these diastereomers. The diastereomers are found in geometrical isomers also. So this is about what? Definition and properties of enantiomers and diastereomers. Now we will see the examples for these enantiomers and diastereomers. Now you take this 2-butanol and this 2-butanol and it is also 2-butanol. Say for example, if it has the dextrorotatory, it will have the levorotatory. Dextro and levorotatory will comes under enantiomers. Now these two are mirror images or not? These two are mirror images. The right side OH comes here left side. The left side hydrogen come to the right hand side. Okay, now these two are non-superimposable on their mirror images. So the two pair of 2-butanol comes under enantiomers. They comes under enantiomers. You take these two also. These two lactic acid just now we had seen. It has the only one chiral carbon is there. Here also. Only enantiomers are possible. For these, no diastereomers. For these compounds, no diastereomers. Diastereomers are possible with more than one chiral carbon. So these two are also pair of enantiomers only. Pair of enantiomers only. Non-superimposable on their mirror images. Now you see here, these two compounds you take here. Okay, now in these two compounds, what happens here? Now you see here, this is head. Now legs you consider. Both are same. But what happens here? The OH is right side. Here the OH is left side. When we are placing in front of mirror, it is a mirror. So then what happens? The OH is right hand side. It appears in left hand side in the mirror. The hydrogen is left here. Hydrogen is present in the right here. Now here hydrogen is right here. The hydrogen is left here. The OH is here left side. The OH is in right side. So what happening? These two are non-superimposable. Now you can take here, this is one hand. If you are placing this one, it will appear like this. Okay, now say for example it is OH, it is H. Now how it is? This OH is going this side, this H is coming this side. So that is what these two are non-superimposable on their mirror images. These two are the pair of enantiomers. These two are the pair of enantiomers. Now here also, here how many chiral carbons are there? This is one chiral carbon, two chiral carbons are there. Now in this case also we have two chiral carbons are there. Here also two chiral carbons. These two also mirror images. These also comes under enantiomers. Enantiomers. Now you take for example this is 1, this is 2, this is 3, this is 4. Now you take here, these 1 and 2 are enantiomer, 3 and 4 are enantiomer. Now you compare 1 and 3. You compare 1 and 3. Is these two are having same molecular formula, so isomers. Are having, these two are called mirror images, 1 and 3. Are these 1 and 3 are called mirror images? No, they are not the mirror images. Now OH is right side. OH is also right side. Now here hydrogen is right side. Here hydrogen left side. Okay, this OH is going. But here the chiral carbon which is not superimposable on their mirror images. Non-mirror images, non-superimposable. So 1 and 3 comes under diastereomers. And also you take the another compound. So you take the 2 and 4 also. You take the 2 and 4 also. 2 and 4 also non-superimposable on their mirror images. They comes under diastereomers. And also you can take 2 and 3 also. You take the 2 and 3 also. They are non-superimposable mirror images, 2 and 3. And also you take the 1 and 4 also. Okay, 1 and 4 also. 1 and 4 also comes under diastereomers. These all will be diastereom. Diastereomers are what? These are the pair of diastereomers. This is one pair, this is another pair, this is another pair, this is another pair. These all will comes under diastereomers. That is, they are non-superimposable. They are non-superimposable as well as non-mirror images. They are called diastereomers. Diastereomers are possible with more than one chiral carbon. Now we will take the tartaric acid here. Now we will take the tartaric acid. Now just you place here tartaric acid, COOH. Here also COOH. Here also COOH. COOH. Now you see in this case, these two are what? Tartaric acids. Okay, now in this case, these two are mirror images. This is 1 and this is 2. Both are mirror images or not? Yes, these two are mirror images. These two are called pair of enantiomers. These two are pair of enantiomers. And also these two also pair of enantiomers. These two are also pair of enantiomers. Now tell me whether these molecules are optically active or not. These two molecules are optically active. Is there any symmetry element is there? Is there any symmetry element when you are bisecting this organic molecule into two equal parts? Are you getting two equal parts? Here the OH is right side, here the OH is left side. So it is not getting the equal part. Okay, so it is what? Optically active. It is also an optically active. But you see here, if you bisect this organic compound, you are getting the two equal halves. So these two are the what? Enantiomers. Even though they are having the symmetry, plane of symmetry, this comes under optically inactive. Optically inactive molecule. Okay, now you take here, this is a 3, this is 4. Now here 2 and 3 are what? Diastereomers. 2 and 3 are diastereomers. So like that you can give the relation 2, 3 diastereomer, 1, 4 diastereomers, which are non-mirror images. This is another example for the enantiomer and diastereomers. I hope so you have understood the enantiomers and diastereomers. Next we are going to see the racemic mixture and Meso compounds. Now we are going to see the Meso compounds and racemic mixture. What is meant by Meso compounds here? The compounds containing 2 or more chiral centers but possessing a chiral molecular structure. That is, it is an achiral molecular structure is there because of having plane of symmetry. If it has the plane of symmetry, definitely it is an optically inactive compound, even though it contains the chiral carbon. Now you see here, so compound containing 2 or more chiral centers but possessing achiral molecular structure because of having plane of symmetry. Now you take in this case, it has the plane of symmetry. Now 2, 3 dibromobutane. In this case, due to presence of this plane of symmetry, this molecule, even though possessing 2 chiral carbon, but it is optically inactive. It is an optically inactive compound. So it is a Meso compound due to presence of plane of symmetry. And here also it has the what? Plane of symmetry. It can break the molecule into 2 equal parts. Above here, whatever the part we are getting, below also same part we are getting. So this also what? It also has the plane of symmetry with 2 chiral carbons. Even though more than 2 chiral carbon, if it has the plane of symmetry, means it is an optically inactive, then such type of compounds are said to be Meso compound. Compounds which are having 2 or more chiral center and possessing the achiral molecular structure due to presence of plane of symmetry. They are called Meso compounds. Now these Meso compounds are optically inactive. Why they are optically inactive? They are having 2 chiral carbons. No? Here what happens here? You take this molecule. Now above molecule is 1 chiral compound. So which rotates the plane polarized light. This molecule rotates the plane polarized light in a clockwise direction. That is what we are calling dextrorotatory or plus rotation. Now this molecule is there. No, bottom molecule will rotate in levorotatory L, or it is also indicated with minus. So then what happens? So this will rotate in anti-clockwise direction. This rotates in clockwise direction. In single molecule, one chiral carbon is rotating the plane polarized light in clockwise. Another chiral molecule is rotating in anti-clockwise direction. Then what happens? Due to that, within the molecule, two chiral carbons are rotating plane polarized right in. One is rotating in clockwise, another one is rotating in anti-clockwise. Both will be cancelled out. It is plus or minus. Both will be cancelled out. The resultant rotation of plane polarized light is 0. That is, it won't rotate the plane polarized light, which is rotating in how much it will rotate in clockwise direction. It rotates in anti-clockwise direction with the same extent. Okay, na? So due to that, that rotation is said to be internal compensation. So meso compounds are optically inactive due to internal compensation. What is meant by internal compensation? In organic compounds having two or more chiral centers, one chiral carbon is rotating in clockwise direction, that is dextrorotatory. Another chiral carbon rotates in anti-clockwise direction within the same molecule. So it is said to be internal compensation. One chiral carbon compensated plane polarized light will be cancelled out by the another chiral compound. Then it forms the meso compound. Next we are going to see the racemic mixture. What is meant by racemic mixture here? It is an equimolar mixture of pair of enantiomers is called racemic mixture, or it is also called racemic modification. What is meant by racemic modification? It is an equimolar mixture of enantiomers. That is what one enantiomer, if you are taking 50% means another also 50%. So equimolar mixture of two enantiomers is taken as racemic mixture. It is also called racemic modification. Now you see here, this compound is there. It is an optically active compound which has the chiral carbons are there, which is not having any plane of symmetry. Is there any plane of symmetry? By cutting this molecule, are we getting the equal parts? Here OH is in right side, here the OH is in left side. So it is not getting the equal parts. So it is not having plane of symmetry also. These two molecules are not having plane of symmetry and they are 50% and 50% compound. Okay, na equimolar mixture of enantiomer. These two are called enantiomers. And equimolar mixture of enantiomers are called racemic mixture. Means, say for example, this compound has the plus 50 degrees rotation. Okay, na? So if it has the plus 50 degrees rotation, its specific rotation is plus 50 degrees. Its rotation will be what? Minus 50 degrees. Okay, na? Its specific rotation is what? Minus 50 degrees. Now you see here both are having the same molecular formula. So if it is rotates in plus 50 degrees means this molecule rotates, this enantiomer rotates in minus 50 degrees. When we are taking equimolar mixture, these both will be cancelled out. Then what happens? The mixture, the equimolar mixture of enantiomers will act as optically inactive compound. Due to one molecule, how much it will rotate? The same molecule will rotate in opposite direction by the plane polarized light. Okay, na? So plane polarized light is rotated in opposite direction by the individual molecule. It is called external compensation. Internal means within the molecule. It is called external compensation. One organic molecule is rotating in plus dextro form. Another one is having the levo form. And both are in equal rotation. Angle of rotation is equal. Both are mixed means both will be cancelled out. That compensation is called external compensation. Okay, na? So due to this external compensation, racemic mixtures are optically inactive. Meso compounds as well as racemic mixtures are optically inactive. These two also optically inactive. These two are the examples of enantiomers. If you are taking equimolar mixture of enantiomers, those comes under racemic mixture. Now indicated by the prefix like D comma L within the bracket or plus or minus within the bracket. Plus or minus will indicate, means which indicates 50% dextro, 50% levo. Here also 50% dextro, 50% levo. That is what we are calling equimolar mixture. Now we are going to see the process of conversion of racemic mixture into optically inactive molecule into optically active enantiomer. That process of conversion of racemic mixture into optically active enantiomer is called resolution. What it is called? Resolution. Now resolution, what is meant by resolution? Just now I told you the process of separation of constituent enantiomeric forms from the racemic mixture into enantiomer, separate enantiomer. That process is called resolution. That is, racemic mixture is converted to optically active enantiomers. That process is called resolution. So racemic mixture is separated into two different enantiomers. That can be done by chemical methods, by mechanical methods, by biochemical method. In chemical methods, what happens? We will add some suitable quantity of some salts we will add. Then what happens? One of the enantiomer will be precipitated, that is separated by the crystallization process, fractional crystallization, fractional distillation process. By using those chemical methods, we can separate them. Okay, now next, mechanical method, which are having magnetic nature. So by using electronic microscopes, we can separate them by using hand also with pair of strands. Next, biochemical method. In biochemical methods, what happens? One enantiomer will be more active, another enantiomer is least active. Okay, na? So whenever some bacteria is sent into that organic compound, so which is high reactive enantiomer, that react with that bacteria and it will be combined with that bacteria, another enantiomer will be precipitated as it is, because it is an inactive one. So that inactive one can be separated from the active enantiomer. Okay, na? So these are the methods which are used for the separation of racemic mixture. The process of separation of racemic mixture into enantiomer from the racemic mixture is called resolution. Now we are going to see the most important number of optical isomers. How we are going to calculate number of optical isomers? Now optical isomers are produced when there is a chiral carbons are there, then only they show the optical isomer, means they rotates the plane polarized light. Now you see here, if molecule is unsymmetrical, if a molecule is unsymmetrical, then what happens? Number of enantiomers, that is D and L isomers, that is nothing but optical isomers will be, number of D and L isomers will be how many? 2 power n. Okay, na? Now number of mesoforms, if it has the unsymmetrical means, so it is not having any plane of symmetry. If it is not having plane of symmetry, then there are no meso products. Okay, now there are no meso isomers. Now total number of optical isomers will be, what happens? We have to add this 2 power n plus 0, that is nothing but 2 power n. Now you take here, n is what here? Number of chiral carbon. N is what? Number of chiral carbon. You take this example here. Is it having any plane of symmetry? Now is it bisects into two equal parts? No. Now the head and the bottom part is different. Then it is not having any plane of symmetry. So it is completely an optically active one. So how many chiral carbons are there here? 2 chiral carbons are there. And also it is an unsymmetrical molecule. So then number of total number of isomers, optical isomers will be, what happens? 2 power n, that is 2 power 2. 2 is what here? Number of chiral carbon. 2 chiral carbons are there. So total number of optical isomers for that compound will be how many? 4 isomers are possible. Now, if a molecule is symmetrical, okay, na? If molecule has the plane of symmetry or the head and bottom parts are similar, then it is said to be symmetrical molecule. Now you take here, it is one of the example of mesotartaric acid. It is taken as one example. Now you take here number of chiral carbon. Number of chiral carbon, when we have even number of chiral carbon, one type of formula is there. When we have odd number of chiral carbons are there, we have different formulas are there. Okay, na? So number of chiral carbons will be how many? Even number, first thing. N is equal to even if you are taking. Then number of D and L isomer will get the what? 2 power n minus 1. Number of D and L isomers will be how many? 2 power n minus 1. Number of meso isomers will be 2 power n by 2 minus 1. It can be written as 2 power n minus 2, 2 power n minus 2 by 2 also. In some book they are written like that. So don't confuse. 2 power n by 2 minus 1 is the formula, or else 2 power n minus 2 by 2. That is the formula when chiral carbon, number of chiral carbons will be even. Now the total number of optical isomers will be, what happens? Total number of optical isomers will be, So we have to add these two. 2 power n minus 1 plus 2 power n by 2 minus 1. That is total number of optical isomers. Say for example this compound, how many optical isomers are there? Here 2 optical isomers are there. Now how many D and L forms are there for that? So that is 2 power 2 minus 1. That is how much it will be? 2 power 2 minus 1 is 2 power 1, that is 2. Number of D and L isomers are 2. How many number of mesoforms there? Mesoforms will be 2 power 2 minus 2 by 2. That is 0 by 2 is nothing but 0. 2 power 0 is 1. So total number of isomers will be what happens? 2 plus 1. That is total how many optical isomers are possible for that mesotartaric acid? 3 number of isomers. When even number of carbons are there, then we have to use these formulas. If we have the odd number of chiral carbons are there, okay na, number of chiral carbons are odd number, then what is the formula we have to see? Listen carefully. Number of D and L forms will get the what? 2 power n minus 1 minus 2 power n minus 1 by 2. 2 power n minus 1 by 2. If you use that formula, you will get D and L forms. Now number of mesoforms you take, number of mesoforms, that is 2 power n minus 1 by 2. Okay now, if you add these two, then what happens? This plus 1, this minus 1 get cancelled. We are going to get 2 power n minus 1. So it is in case of when we have odd number of chiral carbons in a compound. Is that clear? You can find so many examples for this. You can take the glucose molecule. Glucose molecule, open chain structure of glucose molecule has the 4 chiral carbon. For that, you can try these even number. Okay now, so you can try for that. So like that different types of compounds are there. So you can try those, and I will make you separate video for finding number of isomers complete on all structural and stereoisomer at the end of this isomer topic. Okay, have a nice day. Keep watching Appa Chemistry classes. Thank you.